9.4 is odds and expected value. So where have you heard the phrase odds used before? Do you know? Say it. What'd you say? The Hunger Games. Yes, this is new, right? When I first created this lesson, none of that happened. There's somewhere else you gambling. Do you remember? Do you know, Morgan, specifically what kind of gambling uses odds the most? There's a couple of kinds that use it more than others.
Russian roulette or whatever. And
Sometimes you see it with roulette.
poker.
With what? Well, you see the kinds of gambling you guys are describing uses probabilities more than odds.
Yeah.
But there's some kinds of that you really use odds. It's usually in terms of races or competitions. So you think about horse races are always written in odds. The odds are such and such to such and such that this horse is going to win. Sometimes you'll hear odds mentioned in terms of games, like football games, Super Bowl, basketball, these kinds of things, right, where a certain team has so many more odds, the odds for this team to win versus that team to win. Well, there's a relationship between odds and probability, which is why you girls are thinking about odds when we're talking about that particular kind. So odds has this relationship. So if probability of an event happening is P of A, and P of the A bar is probability it doesn't occur, then the odds that the event occur, so the odds of event A is the probability that it occurs compared to the probability that it does not happen. So you're looking at a ratio between two different probabilities. Probability the event happens compared to the probability it doesn't. Now, the odds against, so this is the odds for up here, this is odds against down here. Well, you just flip the fraction upside down. It's the probability that doesn't happen compared to the probability that it does. So we're going to do a real simple, quick example. We've actually seen this happen already. We did an example of this back in chapter 7 or 6, I can't remember which. And so we'll talk about that after we look at this example. Example 1 says, from a set of 8 marbles, there's 5 red and 3 are white, and we choose one at random. This is just like a probability question, right? We could talk about what's the probability of choosing a red marble, what's the probability of choosing a white marble, and we would do it just fine. We're looking at odds, however, okay? So the probability is, or the odds is based on the probability. So what's the probability that we choose a red marble? 5 out of 8. So the 5 is because there are 5 red. The 8 is because what? There's 8 total. If you want to find odds of choosing a red, you're not going to compare the red to the total. You're going to compare the red to the not red, in this case white. But even if there were other colors, we would be comparing red to not red. So how many red are there? 5. How many not red are there? 3. So the odds are 5 to 3. Now, knowing this, we should be able to go back and forth between these two representations pretty easily. I mean, you see where the 5 and the 3 turn into 8, right? And you see where the 8 from above can be turned into the 5 or 3. So there's this definite relationship between these. They're just used in different contexts. Do you remember the example where we talked about, I think it was the number of boys, well, maybe it's the next example. I think we did it before where we talked about comparing the number of boys to the number of girls in a class. That was an example of odds. And I think we did it back in chapter 6. It's been quite a while ago. Let's take a look at another one where we can talk about the comparison between the two. If the probability of rain for the day is 60%, well, what does 60% mean in terms of a fraction? 60 out of 100, or you might express it as 6 out of 10 or something like that. But this is a 60 out of 100% chance. What are the odds against it raining? So we have to talk about odds, right? What did you have for me? Ashley, you said something? Right, so 60 would be the chance that it does happen. We want the odds against. Right, 40 over 60. So the likelihood, yeah, I know, you have to be really careful because that word will kind of sneak up on you. This one said odds against it happening, so you'd have the likelihood that it doesn't happen, that's the 40 or 40%, compared to the likelihood that it does on bottom, which is 60, and this will reduce to what? 2 to 3. So this is a 2 to 3 odds against it raining. All right. This theorem 9.8 actually shows the relationship between the difference for probability and odds. So if we have the probability of an event is m over m plus n, right? So m is the number of ways an event could happen. N is the number of ways it doesn't happen. This is like our marbles example. There were 5 red marbles, and there were 5 plus 3 total marbles, right? And if you wanted the odds against, we could take the 3 that were the white marbles, which was 3, over the 5 plus 3 for the odds against, the probability to give me the odds against this happening. Let's do an example to show you how this relates. This is what we just talked about, so I don't want to spend too long into here. All right, 3-child family. We wrote something out in the last section with the boys and the girls. Do you guys remember that? We did write out a diagram, and I know how much you love those. But we also wrote down, after we did the diagram, just sort of a listing of the orderings. Do you guys remember that? I want to do the listing and the orderings here because kind of like in the Huntington's example where you were talking, Kelly, that it was just 7 out of 8, because every branch is equally likely, right, because they all have 0.5 on them, you could actually just count the different outcomes in the end and say, oh, look, there's 7 compared to 8. And so when there's equally likely chance, you can have that ability to do that. And in this case, that would be equally likely, right? Because boy versus girl when you have a baby. So we have one option when we're having the children of having 3 girls. And then I'm going to sort of in an organized way start changing different pieces of my description. So I could have girl, 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 or I could have girl, girl, boy. And that's the only way I could have 2 girls first, right? So the next thing I need to change is I need to change the second child. So I could have girl, boy, girl, or girl, boy, boy. And these are all of the different ways I could have an oldest child being a girl with 3 kids. So then the other option would be oldest child being a boy. So I'm going to keep going with sort of presuming the girls after that. So I could have boy, girl, girl, or I could have boy, girl, boy. Okay, so I fixed the girl in the middle, didn't change that. But then this is the only ways I can have a boy and then a girl, so I must have another option of having a boy and a girl, or a boy and a boy. So there's actually how many different options here? There are actually 8. And that makes sense again. The reason there's 8 is because we have 3 different stages of the diagram. If we were to do a tree diagram, we'd have 3 different stages. So we have 8 outcomes on the end. Okay? So this one says first, the odds of having all the same gender. So how many here in this list, or what are the ones in this list where they have all the same gender? 2. There's one right here and there's one right here, right? So if we want the odds of having all the same gender, then we would take that number 2 and write it as the numerator. And what would be the denominator?
6.
Is it 8 or 6? 6 when we're doing odds. If it had been 8, we would have actually found what? The probability. Very good. Now this reduces to what? 1 to 3. So the odds are 1 to 3 of having 3 children, 1 out of 3 chance, or 1 to 3 are the odds of having 3 children that are the same gender. This one then says the odds against having the same gender children. So instead of doing 2 over 6, I would do 6 over 2. And as awkward as it sort of feels, when we reduce that, we're going to write it as 3 over 1, and we're not going to reduce it to 3. Because then it would all of a sudden sort of lose effect of what it's talking about, right? So this is one of those cases where, yeah, we're going to leave that 1 in the denominator just like that.
Want us to write it like that or like this?
You have a choice. You could write it like that. Or you could even write it this way with words. Yes, Shayna?
And so you get the 6 instead of the 8 because you take half the 3 and change the 3.
Right. You get the 6 because what you're doing is you're comparing it to not having the event happen that you want. So we're looking at all the ways that whatever we're looking for does not happen, and that's the denominator. It just depends on what you're comparing. Are you comparing the event to the whole sample space, or are you comparing the event to not having the event? That's what odds does. It compares our event to not having our desired event happen. All right, the other section here is expected value. Expected value is basically what you can expect to happen if you performed the experiment a whole bunch of times. Right, so like over time, if you had a gazillion people born in a hospital, you would expect that about half of them would be boys and about half of them would be girls, right? That's the law of large numbers thing we talked about last time. That's the overall expected situation. That's what you're looking at when you're looking at expected value, the overall situation of what happens. However, expected value is used to talk about how you decide how much somebody pays to play a game. That's what it's usually used for, the expected value of some kind of a game situation. So we're talking about lotteries and gambling. This is what's used. So let me show you how this works. The expected value, so these are the different values of the experiment up here at the top, A1 to AN. So they are, the outcome is you lose and you get $0. The outcome is that you win and you win $1. The outcome is that you win and you win $10 million. So these are all numbers. If it's not numbers, what I'm going to write down next isn't going to make any sense. Okay? These are all numerical values assigned to the outcome of what happens. The P's right here are the probabilities of each of those events happening. The likelihood, the chance that it happens. So the way that we find out the expected value, which will in turn tell us something about how somebody should expect to pay for a game, is found by taking the probability times the value. So if the value is A1, we multiply it by the probability of 1. And the value of A2, we multiply by the probability 2. And we keep pairing these up until we get all of the probabilities for all of the outcomes listed multiplied. So all these are is values times probabilities. Values times probabilities. And if a game is fair, then this expected value will be 0. Okay? If the game is fair, the casino wouldn't have the money to build the building or pay its workers. So you can't have a fair game, at least as an overall. The games can't be fair in this sense in a casino, or they wouldn't be an operating business. Are you guys following? I mean, it wouldn't work. Financially speaking, numerically speaking, it would not work. So let's take a look at doing an example. We've got a roulette wheel, and I've simplified the example some, but this is something that actually happens in my husband's family. My father-in-law is a wonderfully sweet man, but this is what he does. On a roulette wheel, the slots are numbered 0, 0, 0, and 1 to 36. So how many places are there on the slot or on the roulette wheel? 38. Okay, so it's just like a spinner. It's a giant spinner with 38 different little slots. That's what it is. Everybody so far good? Okay. And you spin the spinner, and one way to gamble is to choose just which number you think that the spinner basically is going to land on. They do it with balls, but same idea. Where you think it's going to land. You can pick one number. This is one way to play. So the first thing I'd like for us to talk about is this probability. What's the probability that you land on 0, 0? 1 out of 38. We're doing probabilities again, so not odds, but 1 out of 38. When my father-in-law passes the roulette wheel, they actually have on many roulette wheels, maybe not all or most, I don't go into casinos, but I have been in them before. They will have a kind of a board that tells you what has recently been landed on. Okay, so it's kind of like, you know, a history of the wheel. Okay, are you guys good with that? So you can look back and you say, oh look, 2 turns ago it landed on a 7, and then before that it landed on a 7 again. How interesting is that? 7 twice in a row, crazy. So you can look at this sort of a listing of these different outcomes. My father-in-law, no joke, will look at the listing of the history of the outcomes, and if he doesn't see that it has landed on 00 in a while, like the entire board, he'll throw money down on 00. Is it any more likely to land on 00 because of that, guys? So, We're going to see what happens, the expected value of his bet. All right, so let's say, for instance, that the chip, he bets one chip, and the chip is worth $10. So each of the chips is like a $10 bill, okay? The expected outcome of his bet. So the issue is you either win, and you get, it says right here, 35 chips plus the chip you played, or you lose and you lose the one chip. I mean, those are the two outcomes. There's nothing in between on this particular situation. Sometimes there's other options, but on this one, it's just win or lose, okay? So let's start with this one. So the expected value, one outcome is that you lose. And if you lose, what are your earnings? What is it? It's -10. This is the part where people get a little bit tripped up. What you have to remember is that you didn't win 0. You actually lost 10. This is why people lose money in casinos, is they forget they actually paid to play, right? You lost $10 when you failed to land on 0-0. How likely is it that you landed on 0-0? So how likely is it that you did not land on one of the 0-0? There is a 37 out of 38 chance that you lose $10 game's over. Hope that was a fun way to spend your $10. That probably at you guys' age cost you about 2 hours to earn, or pretty close, right? By the time they take away taxes, it's 2 hours for one spin of a wheel. I don't see it as very fun. All right, so the other option is that you win, right, Kenzie? You were telling me this was 1 out of 38, and it's the same 1 out of 38 we did above. Okay, so what happens if you win? $360. Where did $360 come from? Because there's several things in what you did. You're right, but where did it come from?
You get 35 chips, and then you get your chip back, which is 36, and then you times that by 10 because each chip is $40.
Okay, so there's one tiny thing that we want to change about what you said. You pay $10 for the chip. So we don't get to count the chip to be 36, there's just 35. Because that original $10 was already in your pocket to start with. Right? So if they pay you back $360, which they would, $10 of it was already your money to begin with. I mean, like, you gambled it, but you only are actually, if you think about what you're thinking about is, in your pocketbook, what's the difference in your pocketbook? Right? What's the difference from before you started playing the game till after the game was over? Well, that net change in your pocketbook is $350. Yes?
So if it was like a fair game, like you were saying earlier, then they would give you back 39 or 38 chips.
Yes.
Plus your own.
Right. Yeah, if the game were fair, this would actually have to give you back 39 chips. That's right. All right, so let's actually figure out what this gives us. We have negative 370 over 38 plus 350 over 38. I'm sorry, 380. I said 380. I said 38 and then I wrote 380. Let's get the number right. Over 38. All right, so this actually ends up giving me negative 20 over 38, right? Did I screw anything up or is that okay? All right, so this is money. I mean, this is supposed to be money, so I need to know what a numerical number would this look like. What are we talking about here? $sign something, and it's negative. What'd you get, Angela?
I got negative 0.52.
Okay. So the average spin at the roulette wheel costs the average person 52 cents. Now, it doesn't really, right? It either costs them $10 or they win $3.50. But if they played this game a whole bunch of times, on average, their loss would be 50 cents, roughly, per spin, which means that the benefit to the casino would be 50 cents per spin. All right, so they're making money on the game. Are you guys with me? Any questions on this one? Who's playing roulette today? Nobody. This is a bad investment, right? Bad deal. Bad deal. All right, let's do one more. I think we have time for one more. Deal or no deal? Are you familiar with the game? Okay, so the question at the end is not worded well. I think that I've fixed it every single time that I teach it because I forget to fix it in print later. But the first part of the question does start the same. It says, in the television show, Deal or No Deal, a contestant is down to 2 cases with equal probabilities of being chosen. Okay? 2 cases. They have these games like Chuck E. Cheese now. Did you know that? Yeah, they're fun. The cases have either $250,000 in them or $1 in them. And this phrase is terrible. This is because this is what happens when you make up words. This word fair means lots of things to us, right? Have you guys done StrengthsFinder stuff? You guys know what I'm talking about, the StrengthsFinder strengths assessment? Fairness is one of my top 5 strengths. It's a big deal to me. This is why growing up I was always so concerned that we got the exact same number of presents at Christmas and stuff. Fairness is a big deal. All right, so if the game is fair and you're the banker, what would you offer the contestant? Well, it's all based on expected value, sort of the idea of it being, somewhere in between the 250 and the 250,000 and the 1. So if we're looking at expected value or trying to find what the expected value is for the contestant, you have to understand they either win 250 or they win 0 or win 1, right? I mean, it's we don't get the in-between value unless we take the case that's being offered to us. So we're kind of trying to figure out what the in-between value should be as the banker. Everybody good with that? Okay, so we need to find out the probability of choosing each case and the value of choosing each case. So tell me one value of a case. $250,000. What is the probability of that being the winning case, or the case we choose? 1 out of 2. What is the probability, the value of the other case? $1. And what is the probability of that case? 1/2. All right, so we're going to run these numbers, and you're going to tell me what do you get when you take 250,000 divided by 2 plus 1 divided by 2. What is the expected value, or what should the banker offer if he's going to be sort of offering the compromise here in the right way? $125,000 and 50 cents. They don't do that on the show, I know. But this would actually be the expected value of the earnings. So if the game were fair in the sense that it evenly weighted the different options, this is what we would have. This is not what we mean by when we said fair before. I get that. Okay, so ignore the word fair here. Make it sort of like equitable or something like that. Some other word. Any questions on this one? All right. There's exactly one question left. We'll save it for next time.